You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Configuration management provides the backbone of operational security in the cloud by ensuring that resources remain aligned to secure, approved baselines. The purpose of this discipline is twofold. First, to establish authoritative starting points for system settings that reflect both organizational policy and industry standards, and second, to maintain continuous compliance with those baselines as environments evolve. In practice, this means combining proactive measures, such as infrastructure as code validation, with reactive measures, such as drift detection and auto-remediation. Unlike ad hoc configuration changes that introduce inconsistency and risk, disciplined configuration management creates predictability, transparency, and accountability. By embedding baselines into automated controls and documenting every exception, organizations can maintain environments that are not only secure but also defensible in audits and resilient in the face of ongoing change. A configuration baseline is the set of approved settings that govern identities, networks, compute resources, storage, and cloud services. These baselines act as the guardrails of governance, ensuring that critical requirements, such as encryption defaults, firewall rules, or multi-factor authentication, are consistently applied. For example, a baseline for identity management may require short-lived credentials and mandatory MFA for administrative accounts, while a baseline for storage may mandate encryption with customer-managed keys. These defined states become the reference against which actual configurations are compared. Without them, organizations have no common benchmark for determining whether a given system is secure. Baselines create a shared vocabulary and foundation that both technical and compliance teams can align on. Desired state management extends the principle of baselines by declaring target configurations and then continuously reconciling resources to meet them. This approach is often described as self-healing, since deviations from the desired state are automatically corrected. For instance, if a storage bucket's logging configuration is altered manually, the management system detects the drift and restores it to the approved setting. Desired state systems allow organizations to scale configuration control across thousands of resources without relying on manual intervention. They also reduce the risk of misconfiguration persisting unnoticed, turning configuration from a static snapshot into a dynamic, continuously enforced control. This model is especially powerful in multi-region, multi-account environments where consistency is otherwise difficult to achieve. Golden baselines are the authoritative templates derived from external standards such as CIS benchmarks or internal organizational policies. These baselines capture both regulatory requirements and business-specific controls. For example, CIS might require disabling insecure protocols on virtual machines, while an organization's internal policy might mandate tagging every resource with cost center and owner information. By codifying these requirements into a golden baseline, organizations ensure that compliance is consistent and auditable. Golden baselines also provide a starting point for policy as code, enabling automated enforcement at scale. They represent the convergence of external expectations and internal governance, translating both into actionable technical settings. Parameterization allows organizations to apply baselines consistently while still accommodating environment-specific needs. For example, a golden baseline may require encryption on all storage resources, but the key identifiers may vary between development, staging, and production. By parameterizing these values, organizations preserve the intent of the control while flexibly applying it across contexts. This prevents the proliferation of hard-coded, environment-specific baselines that quickly become unmanageable. Parameterization strikes the balance between standardization and adaptability, ensuring that policies are consistent but not brittle. It also supports scalability, since the same baseline can be applied across multiple accounts and regions with minimal modification. Immutable infrastructure is another powerful principle within configuration management, advocating for replace over modify practices. Instead of patching or manually editing existing resources, systems are rebuilt from known good templates whenever changes are needed. For example, if a container image requires a new library version, the approved baseline image is rebuilt and redeployed rather than modified in place. This eliminates drift, simplifies rollback, and strengthens auditability. Immutable approaches also minimize human error, since administrators are less likely to introduce misconfigurations directly. By favoring replacement over modification, organizations maintain consistency and ensure that every running resource reflects the approved baseline exactly. Drift describes the divergence between actual and desired configurations, and it remains one of the greatest challenges in cloud governance. Drift can occur through manual console edits, emergency fixes applied outside change management, or even provider updates that alter defaults. For example, an engineer might temporarily open a firewall port for troubleshooting and forget to close it. Without detection, this drift creates ongoing exposure. Drift management involves identifying, classifying, and reconciling these deviations. In mature environments, drift is not only detected, but also automatically correlated with change records, so that legitimate alterations can be distinguished from policy violations. Drift management is therefore both a technical and governance challenge. Continuous compliance checks are the mechanisms that evaluate runtime configurations against baselines at regular intervals or event triggers. For example, compliance tools may scan IAM policies every hour or run evaluations immediately after new resources are provisioned. These checks ensure that the environment is never left unchecked for long. They also generate evidence for auditors, proving that compliance is not episodic but sustained. Continuous compliance aligns technical monitoring with regulatory obligations, providing a defensible audit trail. It transforms compliance from an annual exercise into a daily practice, ensuring that the environment always reflects approved baselines. Attribute tagging enhances configuration management by embedding metadata into resources. Tags such as owner, environment, sensitivity, and compliance scope provide context that informs posture rules. For example, resources tagged as sensitive may be subject to stricter logging and encryption policies. Attribute tags also improve accountability by tying resources to responsible teams. They enable targeted controls, since compliance scans can prioritize resources based on tags. Tagging is not just an administrative convenience but a governance mechanism, ensuring that baseline policies apply proportionally to resource sensitivity and business value. Access control for configuration stores ensures that only authorized individuals can read, write, or approve configuration changes. For example, infrastructure as code repositories or parameter stores must restrict write access to approved administrators, while read access may be more broadly available for transparency. Every access must be logged, creating a full audit trail. This prevents tampering and ensures accountability. Strong access controls reinforce the principle that configuration itself is a form of critical data, as sensitive to manipulation as application code or customer records. Without access governance, baselines lose their integrity and cannot be trusted as authoritative. Baseline inheritance allows global controls to cascade downward, with explicit overrides permitted only under documented exceptions. For example, an organization may require encryption at rest across all storage resources but allow specific exemptions in test environments where mock data is used. Inheritance reduces redundancy by applying consistent policies broadly while still allowing flexibility where justified. It also simplifies audits, since exceptions are explicitly documented rather than hidden in separate baseline definitions. Inheritance ensures that compliance posture is both consistent and adaptive, reflecting business needs without eroding the overall security model. Pre-deployment validation applies compliance checks to infrastructure as code templates before resources are provisioned. By catching misconfigurations early, organizations prevent non-compliant resources from ever reaching runtime. For example, a template that attempts to create an unencrypted database is blocked during pipeline validation. This shift-left approach saves remediation effort and reduces exposure. It also aligns security with DevOps workflows, embedding compliance directly into the delivery lifecycle. Pre-deployment validation transforms compliance from a reactive process into a proactive safeguard, ensuring that only secure, approved resources are built. Runtime monitors extend validation into live environments by watching control plane, data plane, and application settings for unauthorized changes. These monitors detect when baselines are altered outside approved processes. For example, if an administrator disables logging on a sensitive bucket, runtime monitors immediately generate alerts or trigger remediation. This ensures that compliance posture is not just established at deployment, but maintained in practice. Runtime monitoring closes the loop between configuration intent and operational reality, making continuous compliance possible even in fast-moving environments. Evidence generation is critical for proving that configuration management is working as intended. Each baseline version, approval record, and attestation report must be linked to specific resources. For example, a compliance report might show that a storage bucket is encrypted, supported by the baseline version that mandated encryption and the approval that authorized the baseline. This creates transparency and auditability, satisfying regulators and internal stakeholders. Evidence generation turns compliance from an internal assurance into an externally defensible practice. It ensures that posture is not just claimed, but demonstrated with verifiable proof. Exception workflows provide a structured way to handle deviations from baselines. When non-standard configurations are necessary, they must be documented with risk acceptance, compensating controls, and review dates. For example, if a legacy system cannot support MFA, the exception record would describe why, how the risk is mitigated, and when the system will be phased out. Exception workflows prevent silent, unmanaged drift by ensuring that every deviation is visible and temporary. They balance operational flexibility with accountability, ensuring that exceptions do not undermine the entire configuration model. Time synchronization underpins traceability in configuration management. Logs, compliance scans, and reconciliation events must share consistent timestamps to reconstruct sequences accurately. For example, when drift is detected, investigators need to know whether it occurred before or after an authorized change was applied. Without synchronized time, these distinctions blur, weakening accountability. Cloud environments typically use NTP, but customers must ensure that their workloads also align. Accurate time is not just a technical convenience, but an evidentiary necessity, ensuring that configuration events can be correlated with confidence. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Policy as Code operationalizes configuration management by encoding baseline rules into automated enforcement engines. Instead of relying on human judgment at each step, organizations write policies in declarative formats that can be executed automatically in pipelines and at runtime. For example, a rule may block the deployment of any virtual machine lacking disk encryption, or it may enforce that IAM roles cannot be created with wildcard privileges. Policy as Code tools such as Open Policy Agent or cloud-native equivalents allow these rules to run consistently across environments. This approach eliminates subjectivity and drift by turning governance into software. It also ensures scalability, since the same baseline can be enforced across thousands of accounts and regions without manual oversight. In effect, Policy as Code bridges the gap between written security standards and practical enforcement in live systems. Auto-remediation extends policy enforcement by applying corrective actions automatically when violations are detected. These actions are carefully scoped to be both safe and reversible, ensuring that they do not cause unintended disruption. For example, if a storage bucket is discovered with public access enabled, auto-remediation may immediately revoke that permission while logging the change. The system also generates audit records documenting the violation, the remediation applied, and any associated user notifications. Auto-remediation reduces exposure windows by addressing risks instantly, rather than waiting for human intervention. At the same time, reversibility ensures that if the action impacts legitimate operations, it can be undone quickly. This balance of automation and caution enables organizations to maintain compliance without sacrificing agility or business continuity. Segregation of duties is as important in configuration management as it is in financial governance. To maintain integrity, policy authorship, enforcement administration, and exception approval must be separated. For instance, the engineer writing baseline rules should not also be responsible for granting exceptions to those rules. Enforcement administrators ensure that the policies run as intended, while exception approvers provide oversight when deviations are required. This distribution of responsibility reduces the risk of fraud, error, or unchecked authority. It also creates a system of cross-validation, where no single individual can alter posture unilaterally. In cloud environments where scale and velocity are high, segregation of duties acts as a stabilizing force, preserving accountability and ensuring that governance is not compromised by expediency. Multi-cloud normalization is essential for organizations that operate across providers, each with its own terminology, settings, and APIs. Without normalization, a control such as enforce encryption at rest must be implemented separately for AWS, Azure, and Google Cloud, each with different parameters. Normalization maps these variations to a common control objective and standard metrics, enabling unified governance. For example, whether a resource is an AWS S3 bucket, Azure Blob Storage, or Google Cloud Storage bucket, the control objective remains the same: encryption must be enabled. Multi-cloud normalization simplifies audits by providing consistent reporting across platforms. It also ensures that compliance is maintained holistically rather than fractured by provider-specific silos. This harmonization is critical for large enterprises with diverse portfolios. Configuration drift detection provides real-time visibility into when resources diverge from baselines. Drift detection systems monitor for unauthorized changes, triggering alerts, tickets, or even quarantines depending on severity. For example, if an administrator disables logging on a sensitive service, drift detection flags the deviation immediately, not waiting for a periodic audit. The response may range from notifying the owner to automatically isolating the resource until the issue is resolved. Drift detection ensures that unauthorized or accidental changes are surfaced quickly, reducing the likelihood that they persist unnoticed. By integrating drift detection into pipelines, tickets, and monitoring dashboards, organizations maintain constant awareness of their posture, making compliance continuous rather than episodic. Change correlation strengthens drift management by distinguishing between authorized and unauthorized modifications. Every drift event is linked to requests for change, RFCs, or equivalent records. If the drift corresponds to an approved change, it is logged as legitimate. If not, it is flagged as a policy violation. For example, if IAM permissions are expanded in line with a documented RFC, correlation confirms compliance. But if permissions expand without authorization, the event triggers alerts and investigations. This linkage reduces false positives and ensures that governance is respected. It also builds trust between operations and compliance teams, since authorized changes are not mislabeled as violations. Change correlation demonstrates that compliance monitoring is not adversarial but collaborative. Version configuration artifacts capture every baseline update with diffs, signatures, and release notes. Each version is cryptographically signed and stored, ensuring integrity and traceability. For instance, when a new requirement is added, such as enforcing TLS 1.2 for all endpoints, the baseline update is recorded, along with documentation of why the change was made and who approved it. This versioning creates a transparent history of evolving security posture. It also supports rollback, since previous baselines can be restored if needed. Versioning transforms baselines into living documents that evolve alongside threats, audits, and business needs. It ensures that compliance is not static but adaptable, while still preserving accountability for every change. Data protection baselines focus specifically on ensuring the confidentiality and integrity of information stored in the cloud. These baselines enforce encryption by default, mandate key rotation schedules, and require detailed access logging. For example, an organization may define that all storage resources must use customer-managed encryption keys rotated every 12 months, with logs forwarded to a central SIEM. Data protection baselines also specify access controls, ensuring that only authorized identities can read or write sensitive information. By codifying these requirements, organizations prevent accidental exposure and create a consistent shield for data across environments. Data protection baselines ensure that information governance is operationalized at the technical level, not just the policy level. Network baselines provide a default secure posture for connectivity. They enforce segmentation between tiers, private endpoints for sensitive services, and egress restrictions to limit data exfiltration. For example, a baseline might prohibit public IP addresses on internal workloads, requiring traffic to route through managed gateways with inspection. Default deny policies on security groups and firewalls form the backbone of this posture, ensuring that only explicitly authorized traffic is permitted. Network baselines reduce the attack surface by constraining communication pathways and ensuring visibility through logging. In multi-region and hybrid environments, they also define consistent patterns for routing and segmentation, preventing drift into ad hoc, risky connectivity. Identity baselines establish controls around access management, focusing on least privilege, strong authentication, and credential hygiene. They may require multi-factor authentication for all administrative roles, mandate the use of short-lived tokens rather than long-term credentials, and prohibit wildcard permissions. For example, granting S3* permissions on all buckets would violate the baseline, whereas scoped access to a single bucket would be compliant. Identity baselines are critical because identity is often the first target in cloud compromises. By enforcing rigorous controls, organizations minimize the likelihood of privilege escalation and lateral movement. These baselines anchor trust, ensuring that every action in the cloud environment can be traced to an authenticated and authorized subject. Platform baselines define expectations for compute, managed services, and supporting infrastructure. They may require operating system patch levels, logging coverage, and telemetry export to monitoring systems. For example, virtual machines must use hardened images patched within 30 days. Containers must come from approved registries, and serverless functions must emit logs for every invocation. Platform baselines ensure that workloads not only run securely at launch but remain observable and maintainable over time. They also enforce uniformity across environments, reducing complexity for operations teams. By setting clear requirements for platform services, these baselines elevate operational resilience and simplify compliance monitoring. Reporting brings transparency to configuration management by summarizing control coverage, drift rates, and closure times. Dashboards may show the percentage of resources compliant with baselines, the number of open deviations, and the average time to remediate violations. For example, leadership might see that encryption compliance is at 98%, with 2 critical resources overdue for remediation. Reports also support external audits, demonstrating that baselines are enforced continuously and deviations are tracked to closure. Reporting transforms configuration from a hidden technical activity into an organizational metric, aligning technical posture with business accountability. It ensures that compliance is visible, measurable, and actionable. Anti-patterns serve as cautionary examples of what undermines effective configuration management. Manual console edits bypass pipelines and create drift that is difficult to detect. Unmanaged exceptions allow risky configurations to persist indefinitely, eroding governance. One-time audits without continuous checks provide a false sense of security, since posture can drift the moment after an audit passes. For example, a compliant environment at the time of certification may become non-compliant weeks later if changes are not monitored. Recognizing these anti-patterns prevents organizations from relying on superficial controls. Instead, it reinforces the need for automation, evidence, and continuous vigilance in maintaining secure configurations. Continuous improvement ensures that baselines remain relevant and effective in dynamic cloud environments. Findings from incidents, audit results, and new provider features all feed into baseline updates. For instance, if an incident reveals that API calls were not logged adequately, the baseline is updated to require extended logging across all services. Similarly, when providers introduce new encryption algorithms or identity features, baselines evolve to incorporate them. Continuous improvement ensures that configuration management is not static but adaptive, aligning with both technological progress and threat evolution. By treating baselines as living documents, organizations maintain both resilience and compliance over the long term. For exam preparation, configuration management should be understood as the discipline of defining baselines, detecting drift, and enforcing continuous compliance. Key exam topics include the role of policy as code, the use of auto-remediation, and the importance of segregation of duties in governance. Multi-cloud normalization, evidence generation, and exception workflows are also central to demonstrating operational maturity. Exam scenarios may test whether candidates can select the correct mechanism for maintaining compliance in real time or identify anti-patterns that weaken governance. Success lies in understanding how automated enforcement, versioned baselines, and structured exceptions combine to deliver secure, auditable operations at scale. In summary, configuration management achieves its purpose when versioned baselines, automated enforcement, and controlled exceptions work together to maintain continuous compliance. Policy as code and auto-remediation enforce rules dynamically, while segregation of duties and multi-cloud normalization ensure governance is scalable and defensible. Drift detection, change correlation, and versioning provide transparency and auditability. Data, network, identity, and platform baselines translate high-level security goals into practical controls. Reporting, lessons learned, and continuous improvement keep the system aligned with evolving threats and technologies. By embedding these practices, organizations maintain environments that are not only compliant today but remain resilient and trustworthy in the future. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.